So today is the eighth week of Fundamentals of Power Electronics, the numerical session. So in our last tutorial session, uh, we discussed about the switched mode DC-DC converters. We discussed about the switched mode DC-DC converters, and we talked about some basic converters like buck converter, boost converter, and buck boost converter. So they are the most basic topologies for a DC-DC converter, and all the other DC-DC converters, they are basically derived from these three converters. So those converters that we discussed, they were non-isolated converters, meaning there were no isolation between the supply side, the input side, and the output side. But today we shall discuss some of the converters which are isolated. There will be physical isolation, there will be galvanic isolation between the input side and the output side. The first converter that we will discuss is called the forward converter. Okay, this converter is called the forward converter. This is the topology. This converter is derived from buck converter. How is it derived from buck converter? So I hope you remember the circuit of a buck converter. We discussed it in the last class. So buck converter circuit was like this. So here there will be one semiconductor switch, and here one inductor will be there, and here we had one diode, then here in the output we had a capacitor, and then here we had the load. So this was our input side, P I suppose, and this was our output. And this semiconductor device, suppose we call this S, this can be a MOSFET, this can be a, BJT, or this can be an IGBT, right? So this was the buck converter circuit. Now for deriving this topology, first what is done is this switch. If you see, suppose you just, just suppose there is a BJT like this. There is a BJT. Okay, like this. So what you can see is, if you have BJT or MOSFET or any other device, so these are controlled switches. So you need to give some control inputs in order to turn on the device or turn off the device, right? Some control inputs are there. So some of the devices are current controlled and some of the devices are voltage controlled, that we already studied. So, so this for BJT, we provide some base current, and this is VBE. So it is always like advised that you don't keep this terminal floating. For BJT, the emitter terminal, or for MOSFET, the source terminal, it would be better if you can keep this terminal clamped to the ground. So it is advised so that the gate driver design will be easier. So that's why what is done is we will shift this device from this rail to this ground rail here. So instead of keeping the switch here, the switch is shifted to the ground. So that's why if you see this circuit, here the emitter terminal of this BJT is connected to ground. It is not in the upper side. This is in the downside. So then the connection will be like this. Instead of this, the connection will change to, so let's remove it. So then the connection will be something like this. Instead of keeping it here, we will place this in the return path. So this is will not be here. So the current will come back and go like this. So now this emitter terminal is connected to the ground. Okay. This is one change. Another change is we will have to provide isolation because we want an isolated converter. So that's why we have put a transformer here. So if you see this part, this diode, then this inductor capacitor, this part is identical to a buck converter. Only change is coming. First change that I told, that switch is shifted here. The second change is a transformer is introduced here. So now we have galvanic isolation. So this converter is called the forward converter. This RM and DM, this circuit I will tell later what is the purpose of these components. But for now, this is your converter. This supply VI, then there is this transformer and the switch is there. So basically, I have it is drawn like this. So basically, it will be here will be one DC supply, and this supply is connected like this to the switch. And then in this part, the circuit is similar to a buck converter, right? And here, if you just apply volt second balance for this inductor, because I told you that volt second balance and amp second balance, they are always applicable to any whatever converter you are using. The volt second balance and amp second balance is applicable everywhere. If you apply the volt second balance here, you will get a input output relationship like this. This relationship you will get. So if you remember, for buck converter, the relationship was V out equal to dV in. But here an additional term is there which is N. This N is nothing but the transformer ratio, which is 1:N. So as we have introduced this transformer here, so that's why this N term has come. Otherwise everything is same. The same relationship is maintained for forward converter also, just that you have another degree of freedom which is given, due to which is provided by the transformer. When you will design the circuit, you can select in as per your requirement. Suppose you may want to have a output voltage which is greater than the input voltage. For normal buck converter that is not possible, but here you can select the N in a way so that you can get higher voltage than the input side. Okay, so N is a parameter that gives you additional flexibility for designing the system. Otherwise, this relationship is similar to a buck converter. Fine. And this we derive from the volt second balance. Because here I will just, okay, we discussed this, but anyway, I will just repeat in brief. So we shall discuss the operation. Okay, what happens? So just we will mark this as S, suppose. Okay. So when the time is when the switch is turned on, okay, the switch is on, suppose. Then what happens is this current will flow in the primary circuit like this through the switch. Okay. So as the current flows like this, then due to the dot polarity, there will be some relative positive and negative polarity here. This diode will get forward biased and current will flow like this. Very same, see, it is same like buck converter. There is no difference in the operation. Current will flow like this. And after the DTS period, when you will turn off this switch, then what will happen is the inductor will freewheel. So then the current will flow like this to this diode. Now this diode will get forward biased. So the current will flow in this loop and this diode will be reverse biased, so it will be open, right? So that's how this converter operates. But here one point is that as we are using a transformer, so the flux of the transformer need to be reset, because when in the DTS period, when this transformer it was energized, it was magnetized, then you will give, there will be some magnetizing current, right, through the transformer, and it will get magnetized. But when the inductor is freewheeling, you need to reset that flux. You need to come back at the same point where you started, so that you can start the next cycle. So that's why these additional components are here. This DM, this diode and this resistor is there, so that the it can get demagnetized, right? So here the magnetizing current, like the current will flow in this way, okay, and then it will come back at the same point where it started, and then another cycle will start where again it will get magnetized like this and current will flow through the inductor and to the load like this, and another cycle will be there. Okay, so did you understand the working of forward converter? It is not very different from buck converter. Actually, it is very similar to buck converter. Only change is comes due to the transformer. Okay, otherwise it is same.
And what about the transformer, ma'am? How it will transfer DC power?
No, transformer. See, for transformer also, for transformer, there is a primary winding, there is a secondary winding. So for transformer, as long as you are maintaining the flux linkage same, you don't need to worry about whether it needs to provide DC power or AC power or whatever, right? You don't need to. That's why I said that we are providing this circuit, this diode and resistance, so that whatever magnetization was done in the first interval, it can again get reset via, like, it can dissipate that energy here and it can come back to the same position. Otherwise there will be some flux accumulation and the transformer will get saturated, right? That shouldn't happen. Otherwise it is okay, there is no problem. So if you see the waveforms, it will be clear, I think. I shall show the waveforms. So first of all, see, this point is suppose A. So just for now, just think about this part. So this when there is supply, this switch is on, okay, and this diode is forward bias. Suppose this is D1, this is D1, and this is D2. When D1 is forward biased, then what is the potential of this point? The potential of this point is NVI. If this is 1 is to N, the potential of this point is NVI. And when the switch is off, then D2 gets forward biased. So the potential of A with respect to this point is 0, right? So this gets repeated. And if you see VL, so VL is For buck converter, we saw that the VL, the voltage across the transfer inductor is VI minus VO in DTS period. But here it is NVI minus VO because of this 1:n turns ratio. And when it is freewheeling, then it is minus V naught. Okay. And again, inductor current rises in DTS period because there is some positive voltage across it, and it goes down in the 1 minus DTS period, right? And the load average current is basically the inductor average current. They are same. And this ripple portion goes through the capacitor, same as buck converter. And if we see the current through this switch IQ, so this current basically when this switch is on, the primary current, the current flows through the switch, and the same current basically flows through the inductor. So the current shape is like this. Only it is multiplied by n because there is the transformer in between. That's why. So during DTS period, the current through the switch is like this, just like the inductor current. And then we turn off the switch, so there is no current. The current is zero. Okay. And if you see the D2 current, so it is just similar to buck converter when, because D2 conducts when the inductor is freewheeling. So the current of D2 will only exist when during the freewheeling period. So that's why the current shape is like this, right? So these are the steady state waveforms. Okay. Uh, Now, if we talk about the thing that I was talking about, it is the core reset. How we will do the core reset, right? So you know that for transformer, so there is one magnetization current and there is one load reflected current that we know, right? So when this switch is on and current flows from the supply, then there is both magnetizing current and load reflected current because we are providing current to the load, right? The current is flowing like this to the load. So definitely there will be a load reflected current, and that will be similar to the inductor current here, but with multiplication of n, because due to the transformer. So if the current here is I, it will be Ni here in the primary winding. So this is the current, this portion, this is the load reflected part, and then there will be one magnetizing current that flows through the magnetizing inductance, right? That current is usually very small compared to the load component that we also know. So suppose this is Lm, the magnetizing inductance of the transformer. So the magnetizing current flows through this Lm. For ideal transformer, there is no magnetizing current required, but for practical transformer, very small magnetizing current is drawn. So what is this current? So when we are applying some positive voltage, so that voltage appears across this magnetizing inductance. That is nothing but the voltage Vi. The input voltage appears across the magnetizing inductance. So if you apply a positive voltage across an inductor, what happens? The current rises. So here, if you see, this is the magnetizing current. So the current rises from 0 and it goes to the peak. Okay. And then when you turn off the switch, then the path is broken now, because now no current can flow through the supply through this switch. But now whatever magnetization we did, we need to reset it. So it started from 0. So again we need to make it 0. But what is the path? Because now the switch is not on, switch is off, so there is no path. That's why you need this additional path you have to provide, which is through this diode and through this RM. So now the current was flowing like this in this direction. So the current will continue to flow, but now it will get demagnetized. So the current will circulate here in this loop, right? So that's why you see there is a exponential decay here. Why exponential decay? Because there is RM, right? There is a LM, there is a RM. So this will be an exponential decay. This is a RL circuit. Okay, and the time constant will be time constant tau will be LM by RM. LM by RM. Okay, and that's how it happens in every cycle. So the total primary current, the total primary current will be the summation of this magnetizing current and the load reflected current during DTS period. But during 1 minus DTS period, the current is freewheeling in in the load side. So there will be only the magnetizing current part. So that's why the current is like this. This magnetizing current is only uh, getting reflected here. There is no load component because now load current is freewheeling here due to this inductor. So the current will shape will be like this through the primary winding. And this is the voltage VCEQ. This is the voltage trace uh, on this BJT. So when the BJT is on, then the voltage is 0. When the BJT is off, then what happens is the core reset is going on. So and here we have this supply voltage here like this. If you do KVL in this loop, so if you do KVL in this loop here in this loop, okay, so then you will see the voltage across the device comes out to be VI plus VDM. VDM is the forward drop of the diode plus IMRM, the drop across this resistance. So this is the total voltage that appears across the BJT. And here the core resetting is just started, has just started. So that's why this voltage is like this. This is the peak value, right? Because now IM is at its peak. But then IM gradually reduces. That's why this voltage drop also reduces along with IM. As IM reduces, IMRM also reduces. That's why the drop also reduces and finally it settles to VI, right? Because as the core is reset already, so there will be no current through the diode and no current through the resistance. The only part that is remaining is the input voltage. That's why it settles to input voltage, right? So and one point that needs to be that is very important is that you need to provide sufficient time for core resetting. So that's why for forward converter, it is told that the maximum duty that you can have is 0.5. Because beyond, if the magnetizing current you are giving for magnetization, that is 50% of your time period, then the same amount of time you need to give it to for resetting. So that's why 0.5 is roughly the margin for duty in forward converter because you need to provide that sufficient time for resetting the code, right? So, yeah. So I hope you understood the concept of core resetting. So here we are able to use a transformer even though this is a DC-DC converter because we are resetting the code. Whatever flux is accumulated in the DTS period, we are resetting it, right? So there is no harm in using a transformer here. It can work perfectly fine in for a DC-DC converter also. Even though the supply, the input is DC and the output is also DC, right? So now we shall see some design equations. I told that the tau, the time period, the time constant is Lm by Rm, where Lm is the magnetizing inductance and Rm is the resistance that we externally put in the resetting circuit. So 5 times the time constant, that is roughly the time to uh, for roughly the time that is required for core resetting. So that should be less than or equal to 1 minus dTs. So if your so you have to select the duty ratio accordingly so that this 5 tau should be less than or equal to 1 minus dTs. This time is required for core resetting. Another condition is this voltage. Basically, this value I am talking about, the peak voltage that appears across the device, that should be less than the switch breakdown voltage. For BJT, it is VCEO. For MOSFET also, there will be some voltage that it can withstand, beyond which it will fail. So this peak value should be less than VCEO. From these two inequalities, we get this relation. So from this relation, you can design RM. The resistance you can design from this relation. And another thing is when you will select a resistance, the value is not sufficient. You also need to know the power rating of the resistance, right? So what is the power rating? The power rating should be at least half Lm Im square, because this is the Im, this is the current Im. So the energy stored in the inductor at this point is half Lm Im square, right? So your resistance power rating should at least be half Lm Im square or greater than this. So these relations you need to remember while designing the forward converter. Okay. Yeah. Another thing is that so there is a disadvantage of this kind of co-resetting circuit. What is the disadvantage? The disadvantage is that this is a lossy solution. Why? Because we are providing this resistance here. So there will definitely be some loss here. There are circuits where we don't have to incur any loss, but still we can reset the code. So this is one such circuit where the resetting circuit you use there, you need additional winding and a diode, but there is no lossy component like the resistance. So this core resetting circuit is also used. So how does this work? So here, as I told that you have one additional winding and the turns ratio would be 1:1:n. So this the same number of turns you will use for this primary winding also and this winding also. Okay, and the diode is connected like this. So if we just draw this circuit for our ease of understanding, this is our supply voltage or input voltage, suppose. And here we have this winding here, primary winding. And here we have our switch. Okay. And then here we have another winding which has same number of turns as this one. And here we have a diode which is connected to the supply ground. And but just note the dot polarity here. The dot is opposite. If the dot is here for our circuit for the primary, if the dot is here, for this winding the dot is here, right? So see, when switch is on, suppose we have this is on, so the current flows like this. Okay, so the current flows like this. But current can't go through here because, like, if suppose this is plus and this is minus, so what would be the relative polarity here? It would be plus, it would be minus, right? Like this. But when you turn off this switch, then the polarity reverses because you are interrupting the current through this winding. So there will be some di by dt and the polarity gets reversed. It becomes positive here and negative here. So here also the polarity will be opposite. It will get opposite. So here it becomes negative. Here it becomes positive, right? So the current was flowing like this. So here, how will the current flow? The current will flow like this. So from here to through the supply through this diode, right? So the magnetization current will circulate like this until it gets reset, until it gets zero. It will keep on circulating like this in this path from this winding to the supply through this diode and back to the magnetizing inductor. Okay. So this will be the path. And here you don't have to incur very high loss because there is no resistance here. So this is a lossless pole reset circuit. And there is another isolated converter which is called the flyback converter. This is a very popular converter, popular isolated converter. I think some of you must have heard about it. This is very popular and this is used like very predominantly in industry and for various applications. But this is a low power converter. You can't use it for very high power applications. But yeah, this is a very popular converter. And this converter is derived from buck boost converter. Okay. Like forward converter is derived from buck converter. This converter is derived from buck boost converter. Its working principle is very similar to buck boost. For buck boost, what happens? So buck boost converters configure the buck boost converter I have shown here. So there will be two devices. Okay. So earlier last class I told you that just by changing this inductor position, we can get buck converter or boost converter or buck boost converter, right? So now the inductor is connected like this. Here will be one semiconductor device. When the semiconductor will be on, the device will be on, the inductor will get energized like this in this path. And then this, there here we use a diode. Here we use a diode for buck boost converter. So the diode will be reverse biased and the load current will be provided by the capacitor. And when you turn off this switch, then the path is interrupted. Now the inductor current will freewheel in this path through the diode. It will freewheel like this. So here basically the polarity becomes like this. The output voltage polarity is like this. And I have also written the volt second balance equation. When this switch is on, the voltage across the inductor is V in, this supply voltage basically. So V in times dTs plus V naught times 1 minus dTs is 0. And V naught becomes minus d by 1 minus dV. Why minus? Because the current is flowing like this, so the output voltage polarity is something like this. Instead of our conventional here plus here and minus here, we are getting a voltage polarity like this. That's why this minus sign comes here. So this is the buck boost converter, and here in the for the buck boost converter we can get buck action also, where the output voltage is lesser than the input voltage. We can get boost action also, where the output voltage is greater than the input voltage. Okay, so that's why it is called buck boost converter. And here some waveforms are shown here. These waveforms I have taken from the lecture slides only. So you can go through the lectures by one answer. So this is the inductor voltage when during DTS period when the switch is on. This is V in, and when the switch is off, it is V out like this. So the volt second balance is maintained here. And the inductor current is again when there is some positive voltage, the current rises, and some negative voltage is here, the current has negative slope like this. And IT1P means the current through this switch. So the current through the switch will be only be there when the switch is on. So this is exactly like the inductor current during DTS period, and during this period it becomes 0. And the diode conducts during 1 minus DTS period. So it is 0 here and exactly equal to the inductor current during this period. Okay. And this is the capacitor current. Now you see this current is basically during DTS period. I told you that the inductor gets energized in like this, and the load current is provided by the capacitor. That's why the current is minus I naught. This is minus I naught because the capacitor is giving the load current. And during 1 minus DTS period, it carries the ripple portion like this. Okay. So here also amp second balance is maintained for the capacitor. Now we will see how the flyback converter works. Okay. So this is the flyback converter. So if you see here again, the same thing has been done. The switch has been shifted to the negative rail, and the emitter terminal is connected to the ground. And here there is this isolation is provided, but here this acts as an inductor only. Basically, this inductor, if you just think of this inductor, and if you just use a core here and you provide another winding like this, that's how we get to the flyback converter. But it's operating, it acts just like an inductor. So during some time it stores energy, and in the next interval it dissipates the energy. So its operating principle is same as the buck boost inductor, just that we have provided an isolation here. Okay. And then the rest of the things are here. The dot is reverse. Here the dot is here in the this winding. The dot is here. So and here we have the diode and the capacitor and the load like the buck boost converter. So basically, when this switch is on, when Q is on, then the current will flow like this in this path, and it gets energized. Right, the inductor gets energized. What is the polarity? The relative polarity is plus here, and minus here. So here as the dot is opposite, so here we will get plus and here we will get minus. That's why the diode is reverse biased in this interval during DTS period I am talking about. Now the diode is reverse biased, so the current is provided by the capacitor. Just like buck boost converter, where during DTS period the inductor gets energized and the load current is provided by the capacitor. And in the 1 minus DTS period, what happens is you disconnect, you turn off the switch. So now this inductor, this polarity gets reversed like this, and it becomes plus, it becomes minus, and now the diode can conduct. So now the diode conducts and current flows in this path. Okay. So now this basically in the DTS period it gets energized, and in the 1 minus DTS period it dissipates the energy via the load. Okay. So the waveforms are like this. So we are talking about the voltage across this winding. So it is Vi when the switch is on, and it is V naught by N because of this 1 is to N transformer ratio. Here it was what? Vi and V naught. Here it is V naught by N because of this turns ratio. And this is the flux waveform. So the flux rises here and it goes down and comes back to the same position. Again it rises and comes back to the same position. This is the average value, suppose. Okay. This is IQ because only during DTS period the switch is on and it conducts current. So this is IQ, and this has the same slope as the as the inductor that we were talking when we were discussing the buck boost converter. So this is VI by L because when the switch is on, VI, the voltage VI is the voltage VI appears across the primary winding, right? So this is on. So there is no voltage drop across the switch. This input voltage comes across this winding. So the slope will be VI by L. The current slope will be VI by L. And then it is 0 during this interval. And ID will be again during 1 minus D period. This diode conducts. So it is like this with a falling slope of V naught by N square L, like this. Okay. And this is the capacitor current. So this is same as buck boost. This is I naught, and then the ripple portion is carried by the capacitor like this. So the current is like this. Okay. So these are the waveforms for flyback converter. Okay. So I hope you understood. And you go through the lectures also. They are it has been discussed in more detail. And as I have to discuss the numericals also, that's why I can't go to, like, I can't discuss very elaborately. You go through the lectures and you will understand better. Okay. So here, just remember one thing here, although there is isolation, but this acts as an inductor rather than a transformer. Because in transformer, if some primary, your primary VA is equal to secondary VA. So whenever you transfer some energy here, simultaneously the energy gets transferred to the load. But here, in one interval, it gets energized, and in the next, it stores that energy, and in the next interval, it dissipates that energy like an inductor. So it acts as an inductor rather than a transformer. Okay. So you need to understand this for a flyback converter. Okay. So I think now the time is 6:52. So let's take a 5-minute break. Then I shall resume the problem solving. Okay. Meanwhile, if you have any question, you can ask me. Okay. You can ask me after the break, or otherwise I shall resume the problem solving. Okay. Do you have any question on so far whatever we have discussed? The forward converter, the flyback converter, their operation. If you do not have any question, let's start the numericals. The first problem is a flyback converter is supplied from a battery of 25 volt. The voltage across the load is 25 volt and it is drawing a current of 1 ampere. The flyback converter switch is operating at 25 kilohertz and at a duty ratio of 0.6. What should be the minimum voltage withstanding capability of the switch is in volts. We need to find out what should be the voltage withstanding capability of this switch. The minimum voltage withstanding capability. So these calculations are necessary because when you will design an actual circuit, then you need to select some device. So there you need to select what will be the maximum voltage rating of this device, voltage withstanding rating, what will be the current. So that's why you need to calculate all these things so that you can select the proper device with proper ratings. So this is a flyback converter. Here the input voltage is given, the output voltage is given, the output current is given, the switching frequency is given, the duty ratio is given. So many data is already given. So first what we need to find out is the simplest thing, that is what is the, so for flyback converter we saw that the, I think I didn't discuss it here, the voltage across the flyback switch, that I didn't discuss. So when this switch is off, basically during 1 minus dTs period, when this switch is off, what is the voltage that comes across this switch? So if you see the circuit here, current is flowing like this. Now this diode is on, so there is no voltage drop, and the potential of this volt point is V naught, V out. So this V out voltage comes here also. So this V out voltage comes here also with this polarity. Now, as this secondary winding voltage is V naught, what will be the voltage here? The voltage here will be V naught by N, right? If the turns ratio is 1:N, the voltage in the primary winding will be V naught by N with this polarity, plus here and minus here. And this is V input. If you then do KVL in this loop, in this primary loop, the voltage across the switch VQ is what? VQ is VI plus V naught by N. That is the voltage across the switch. So this is one drawback of flyback, that this device needs to withstand a large voltage. Not input voltage plus V naught by N. Okay, so the voltage rating of this device needs to be quite large for a flyback converter. Okay, so here you have everything, right? You have V input, you also have V output, but here the turns ratio is not given, right? You need the turns ratio for finding out the voltage across the switch. So that's what has been done. So the relationship of input voltage and output voltage for a flyback converter is this. Similar to the buck boost converter with this additional N. This N we are going to find out. So D is given, V out is given, V input is given, and N comes out to be 0.666. And when the switch is off, then what is the voltage? The voltage across the switch is input voltage plus V naught by N. So we know N, the voltage, now the voltage is, this is 25 and N is this. So this comes out to be 62.5 volt. Okay. This is the voltage. So this is the minimum, this should be the minimum voltage rating of the switch. So whenever you will choose an actual device, preferably its voltage withstanding capability should be higher than this value. There we usually keep some margin. So whatever switch you will select, the voltage rating of that switch should be higher than this. Okay. This is the minimum value that it should withstand. Like that should be its rating. But usually we choose a higher value for the voltage rating. So let's see the next question. Here, this figure shows a schematic circuit of a multi-winding flyback DC-DC converter. What are the values of output voltages VO1 and VO2 respectively at a given duty ratio of 0.6? Consider all the components as ideal and the diodes to be identical. So here we studied flyback converter, but there we saw only one winding, one primary winding, and we saw one secondary winding. But here there is additional winding, the tertiary winding is also there, and here we get two output voltages, VO1 and VO2. These are called multi-winding flyback converters, where you get multiple output voltages. Okay. So this is also very popular. If you see some application note of Texas Instruments or some other Infineon or something, you will see you will see this kind of topologies where there are multiple output voltages. Okay, so this is a multi-winding flyback converter. Here, what information do we have? We have the duty ratio information, and the components are ideal. We need to find out VO1 and VO2. Okay, so let's see. Yeah, so I think, yeah, so the input voltage is given here in the diagram, 24 volt. Here we can use this relationship straightforward for finding out VO1 and VO2. So this turns ratio is 1:2 for this winding, and for this winding it is 1:3. So suppose it has one turn, then it will have two turns, this winding, and this winding will have three turns. That's what turns ratio means. So this ratio will be maintained irrespective of whatever is the turn number. So if this is 10, it would be 20 and it would be 30. Okay, so that this 1:2:3 turns ratio is maintained. So this output voltage will be what? V01 is N1 D by 1 minus D into V. So N1 here is 2 because this is 1:2. So this is 72 volt. And for the other winding, we can calculate the value similarly into, that is 3 because this is 1:3. So this is what? This value is 108 volt. Okay. So what would be the correct option? The correct option is option B, 72 volt and 108 volt. Okay. So let's see the next question. What is the peak voltage stress across the switch in the circuit? So what is the peak voltage stress? So again for flyback, we already saw what is the voltage stress V in plus V naught by N. Okay, that is the peak voltage stress across the device. Here we have two output voltages. So you can take any of them. You can take any of them and you can calculate the switch peak voltage stress. So this is 24 and V naught. Suppose you take this V naught. So this we found out. This was V naught one was 72 volt in the last question. This was 72 volt and this was 108 volt. This was 108 volt. So you take, suppose we take 72 volt. So 72 and the turns ratio is 1:2 and this is 1:2. So by 2. So this is 36. 36 plus 24. That is 60 volt. Okay. You can also calculate this with 108. So it would be 108 by 3 for this case. It then also it will get 60 volt only. So the correct option is 60 volt. Okay. So here I have written it. So 1 by N2 V naught 1. So this would be N1. Yes. Mm. Mm. Yes, so this is 60 volt. Okay, this is the correct option. So is it okay? Who understood, right?
Yes, ma'am, I understand.
Yes, ma'am, got an idea.
Okay. Basically, voltage trace is what? Like when the switch is off, it blocks some voltage. So whatever voltage it needs to block, that is its voltage trace. So when we choose the device, we choose a device which has a bit higher voltage withstanding capability than our requirement, just to have some margin. So that's why this voltage trace, we should know what should be the voltage trace. After that only we can select the device. Otherwise, what will happen? The switch will break down. Okay. So that's why these calculations are important. What is the next question? The next question is what is the peak inverse voltage across the diode D1? This diode. There are four options are given. So here you will have to apply the same logic. So for this diode, we will have to consider the time when the diode is not conducting. That's when it will have to block some voltage, right? So when it doesn't conduct, when this inductor is getting energized via this switch, that's when this diode is open and it blocks some voltage. So when the current is flowing like this, here we are getting 24 volts, the input voltage. Here we are getting 24 volts and the dot polarity indicates that the polarity will be here like this and this, and the diode here is reverse biased. Here in this point, the potential is V naught 1, right? It is V01 is always maintained because we have this capacitor filter here. So this is V01. And here we have this 24 because there is a turns ratio here. So you need to consider it. So it will be what? 48 volt, right? Because this is 1:2. So this will be 48 volt. And if you consider this loop, so the diode PIV will be, peak inverse voltage will be, PIV will be, so apply KVL here. So suppose this is my diode voltage. So plus here, plus, plus. So it will be what if we just consider the magnitude, it will be 48 plus this output voltage was 72, right? 72. So it is 120 volt. 120 volt is the peak inverse voltage of D1, right? So for D1, if you want the expression is in V in plus V out. That is the peak inverse voltage across the diode. Okay. If you want to find out for this diode also, you can find it in a similar way. So here, this voltage will be what? 24 into 3, right? Because here the turns ratio is 1:3 for D2. This is for D1. This is PIV of D1. And if we want to find out PIV of D2, for D2, the same way you can find out 24 into 3 in VI plus the output voltage that was 108. 108. So this is what? Can you calculate? This is 72 plus 108. I think so. It comes out what? 180 volt, right? Yeah. So
Yes,
this
ma'am.
is 180 volt. 180 volt. So this will be the peak inverse voltage of the D2. So if you want to choose a diode, you will have to see what is the peak inverse voltage of that diode, and it should be at greater than 180 volt. Okay. So you need to take care of these things while choosing the diodes and the switches. I have calculated it here. And let's go to the next question. What is the question? Okay, so for designing a flyback converter, sourcing power from 20 volt input voltage. So here we already have been, and supplying it to 10 ohm load. The load resistance value is given here. The duty ratio is 0.4. Turns ratio is 4. Find the load voltage VO and the minimum value of the inductance LP seen from the primary side. What other informations are given? The switching frequency and the current ripple through the transistor when it is conducting is less than or equal to 10% of input average current. Okay. And the options are given here. So we have input voltage, we have the load resistance value, duty ratio value, the turns ratio, and we have the switching frequency, and we have this specification that our current ripple through the transistor is less than or equal to 10% of input average current. Okay, let's see. So first, we can find out what is our output voltage, right? For flyback converter, this is the relation N into D by 1 minus D into input voltage. We know N, we know D, we also know V. So we can find out this is what is the output voltage, that is 53.33 volt. Fine. And we have the load resistance value 10 ampere, 10 ohm. So what will be the output current? 5.333 ampere, right? Now here we have a turns ratio. So before that, from power balance, suppose we are assuming an ideal circuit where input power is equal to output power. So V in times I in, that is the input power, should be equal to the output power, which is V out times I out. So we know V in and we also know V out I out. So we can find out what is input average current. But mind, this is average current, right? This is the average current value because our current is not continuous, right? So this average value of this input current is 14.22 ampere. You can calculate it on your own. You will see that this value we get. And there in the specification, they have told that our current ripple through the transistor means this through this switch. They are saying through this transistor is less than equal to 10% of input average current. So 10% of input average current is 0.1 times this, so 1.422 ampere, right? And now if you see when the switch is on and this inductor gets energized, so the question is what will be the equivalent inductor value seen from the primary side? So there is some magnetizing inductance here and it gets energized, right? During this DTS period. Suppose that inductance is LP. So LDI by dt is equal to voltage that we know. This is the fundamental principle. LDI by dt is equal to VL, right? So here DI is delta IL, that is the current ripple, and dt is duty times the time period, because during this interval only this gets energized. That value is V in, because the voltage appearing across the winding is V in. So we know delta IL from here. We know the duty value. We know TS because they have given the switching frequency 100 kilohertz. So TS is 1 by Fs. From here we can calculate, so IL delta IL should be less than or equal to this value, and all the other values are known. From here we can find out LP, the inductance seen from the primary side, which should be at least which is greater than or equal to 56.26 microhenry. Okay, this is the inductance value. So the correct option is option C, this one. This is the correct option. Output voltage is this and LP is 56.3 microhenry. Okay. So did you understand?
Yes, ma'am.
Okay. Okay, fine. Let's go to the next question then. Mm, so this is a big problem. Like the question is big. What are the design specifications and parameters for a forward converter delivering 25 watt output power to a resistive load RL, considering The parameters are given. The turns ratio is 2. Input voltage 100 volt. Switching frequency is 100 kilohertz. Load resistance is 100 ohm. Design consideration for inductor L is to achieve a peak-to-peak ripple of 10% of load current. Again, the ripple specification is given 10% of the load current. The magnetizing inductance value is 0.5 millihenry, and all the diodes are assumed to be ideal. What is the peak current flowing through the primary of the forward converter expressed in amperes? With so all the specifications are given, so you need to find out the peak current through the primary winding of the forward converter. Okay, so when we were discussing the forward converter, so I showed you the waveforms. So the primary winding current, the current that flows through the primary winding, that consists of two components. One is the load reflected component, another is the magnetizing current component. Okay. So the load reflected component comes because in the load side, some current is going via this inductor to the load. So that component gets reflected to the primary side, and that's what we get here with the turns ratio properly inculminated in this calculation. And along with that, we also get some current due to the magnetizing component, because in every transformer there will be a magnetizing inductance, and for the magnetization of the transformer it will draw some current. So that is the magnetizing current. This current gets added up with this load component, and we get this current. And during this period we only have the magnetizing current because now this switch is off, so there is no load component here. So we need to find out this value. What is the peak current through the primary winding? This is the peak current through the primary winding. For that, we need to find out the magnetizing current value Im, this value Im, and we need to find out the peak current value of this load component, which is this one, right? So let's see. Uh, so what informations we have? They provided the output power, and they also provided the load resistance value. From here we can find out the output voltage value. So this comes out to be 50 volt. It was 25 watt, 25 watt, and this was 100 ohm. 100 ohm. So the output voltage is 50 volt. Okay. For forward converter, this is a buck derived converter. So the input output relationship is this. We know V out, we know V in, we also know N. N is given what? N is given 2. So what is the duty ratio value? We can calculate. The duty ratio value is 0.25. Delta IL is given. What is delta IL? 10% of load current. So this is 0.05 ampere. So the maximum current through this diode. So through diode D1, what is the maximum current? I naught plus del IL by 2. Right, this is the maximum current. So we have so the what will be the reflected value? The reflected value will be n times this value, because you want the reflected current through the primary winding. That's why we need to multiply with n, and we get this value. So we have already got this value, this point. Now we need to find out this point. What is Im? When when the switch of the forward converter is on, right, then the primary winding gets energized, right? So that's why this current rises like this. It has a positive slope like this. The voltage that comes across the primary winding is what? Input voltage, right? And the time period is dTs. So d by fs, dTs or d by fs, they are basically the same. And the magnetizing inductance is Lm. This value is given 0.5 millihenry. So from here you can get the value 0.5 ampere, the magnetizing current. So if you just add these two values, you will get the peak value through the primary winding, 1.55 ampere. So this point is, just a minute. So this point is 1.55 ampere. Okay. This is 1.55 ampere. Right? Okay, so let's see the next problem. What they are asking. What is the minimum voltage withstanding capacity required for the primary power semiconductor switch in a forward converter that utilizes the lossless flux reset topology, is supplied from a 72-volt battery, operates at a duty ratio of 0.4 and a frequency of 25 kilohertz with a load voltage of 15 volt and load current of 1 ampere. So this is 72 volt, the input voltage, and the output voltage and output current is given. Output voltage, output current, switching frequency, duty ratio. All these parameters are given. And this loss reset, the core reset circuit is the lossless circuit that I showed you. So here this additional winding is there, which has the same turns, number of turns as this primary winding. And there is this diode. The diode is here. So when there will be requirement of core reset, the current will flow in this manner through the supply and the core will get reset without any significant loss, right? So what they are asking, they are asking that what should be the voltage withstanding capability of this power semiconductor switch, means this switch. Okay, let's see. Yeah. So this is straightforward. So just I will just show you the waveforms that will be advantageous. Just a moment. So this is the same waveform. Okay, the core resetting part here. Okay, so the operation is same. Whether you use a lossy core resetting circuit or a lossless core resetting circuit, the point is you need to reset the core flux. You need to wherever the flux is starting, it should get back to the same value before starting the next cycle. That is the point. So here When you were turning off the switch, then I told you the operation that the polarity becomes like this, the polarity reverses and it becomes like this, and the current flows like this, right? So if you just apply KVL in this loop, the point is whatever voltage comes here, the same voltage will come here because the turns ratio is 1:1. The number of turns is same. So whatever voltage comes in the winding, the same voltage will be induced in this winding also. So when this co-resetting is happening, what is the voltage that comes across this winding? That is 72 volt, right? We are assuming the diode as ideal, so the entire voltage comes across this winding. So here also you will get 72 volt with this polarity, right? With plus here and minus here. So if you apply KVL here in this loop, so what will be the voltage? The voltage will be this V in. So you can follow this loop also or this loop also, same thing. So here it is minus to plus, so 72. Then here also minus 2 plus 72. So the voltage across this device is 72 plus 72, 144 volt. Right. You can use this loop also or this loop also. You will get the same thing. Here also 72 volt, here also 72 volt, but the dot polarity is opposite. So these two voltages gets added and the summation of these two voltage appears across the switch. So this is 144 volt. Okay.
How both are added, ma'am? V in plus V reset. How we getting that?
Because due to the polarity. See here the dot is here and for this winding the dot is here. If the relative polarity during the resetting is this for this winding it is plus and this is minus. Right. So this is 72 volt and this is also 72 volt, just that the polarities are opposite. So if you just take this loop from starting here to here to here to here, okay. So what you will get? Suppose this is minus, this is plus. So minus suppose I am calling it V primary, VP. So minus VP, then this is the switch voltage. Suppose this is V switch, VSW, okay. And then again you are going from minus to plus for this supply. So this is again minus V in and this is 0, right? This is the KVL. So VSW is what? VP plus V in. So V in is 72 and VP is also 72 because 72 volt is appearing here. So as per transformer operation, 72 volt will also come here because their turns ratio is 1:1. So that's why it is 72 and 72 they get added up, right? You understood? So this is from minus to plus, like whatever convention you want, you can do. You can have the convention where you will consider this plus. So whatever convention you follow, you will get this value only. Okay. As these polarities are like this, the dots are placed like this. That's why these two voltages get added up. But if the dot would have been like this in this portion, then it will not be like this. Due to this dot convention only, we are getting this added voltage, right? So if you follow this loop, if you don't consider V, you follow the loop within these two windings. Here also you will get the same thing. So here minus to plus, some this is
Ma'am,
minus.
can you use that highlighter? We are unable to see. You're telling so you're placing your cursor somewhere, but we are unable to follow that.
Acha, acha, right.
Uh, no,
Sorry.
no, the other one.
Ha. Understood. Pointer you were saying. So instead of this bigger loop from here to here to here, you can also apply KVL in this loop. So here also you see minus 2 plus. So this will be minus 72, then plus V switch, then again minus 72. This is minus, this is plus. So again you will get 144 volt only. Okay. 144 volt will come across this switch.
Is there any possibility like dots will change the direction
No,
in forward converter?
actually we wind the transformer in a way so that like dots are what? This is just a convention. So what we assume is whenever some voltage is applied across this transformer winding, wherever there is dot, so if the dot is placed here and the dot is placed here, so their relative polarities will be same. If this is positive, this will be positive. If this is negative, this will be negative. That is the dot convention. Now, whenever we wind this transformer, we wind this in a way so that the sense of this winding and the sense of this winding are different, so that their polarities are different. Okay, so we wind when you will wind the transformer, you will wind it like suppose this is clockwise, you will wind this in anti-clockwise fashion so that you get this dot convention, this dot polarity. This is just a way for representing the windings, right? This is a convention, nothing
Okay, good.
else.
Thank
Hmm.
you.
Huh. Yeah. So this is nothing. So this we discussed forward converter is derived from this is a buck converter. So sorry.
To toggle with P, ma'am. If you press alphabet P, it will change to pen mode.
Yeah. Sometimes these keys are not working. Actually, my laptop is a bit old.
Okay, okay.
Uh, okay, let's see this question. Uh, what is the resistance value required for the freewheeling action of the magnetizing inductance to maintain a time constant of 0.25 Ts? In the off state where Ts represents the switching time and it has a value of 50 microsecond, right? And assume the diodes are ideal and the transformer has no leakage. So again, this is the co-resetting circuit, but the lossy one where we are using this resistance that I showed first, right? This is the lossy co-resetting circuit. So they are asking the resistance value. So while discussing, I discussed some equations through which you can design this R, right? I discussed some equations. Using those equations only, we can get the value of R. So these informations are given, the output voltage is given, the resistance is given, the input voltage is given, this magnetizing inductance value is also given. But here we don't need all these things. This question is very simple actually, the first part. So the time constant is Lm by Rm. Lm is the magnetizing inductance, Rm is the resistance. And that is given 0.25 Ts. Ts value is 50 micros, so tau is 12.5 microsecond. If you have the tau value and you already know the value of Lm, so you can find out value of R, which is 8 kilo. This is very straightforward, right? So you don't need the output voltage or the input voltage value or anything. This is just this very small numerical. In the second part, what they are asking, the scenario described in question 9, what is the peak voltage drop by the switch in the circuit? So now you need to find out what is the voltage drop across this switch. Now you need all these informations. So V naught is NdV in for forward converter. Duty ratio is 0.5. Why? Because you know the V out value, you know the V in value. You also know what is N. N is 1:1. So D value, what is D? D is 0.5 from this equation. Now you need to find out the magnetizing current, right? What is the magnetizing current? The magnetizing current is V in D by LMFS. Because when this switch is on, this gets magnetized, right? The magnetizing current flow through this transformer, and the voltage applied across the magnetizing inductance is V. So LdI by dt is equal to V, where your del I is nothing but the magnetizing current because it starts from zero, and your dt is dts. Dts is d by fs. So from here you can find out what is the magnetizing current value Im, the peak value basically, that is 0.012 ampere. And therefore the voltage across the switch is what? V in plus IMR. So IM you calculated, V in you know, that is 144 volt. V in is 48, IM is this, and R is we calculated 8 kilo ohm. So your voltage across the switch is 144 volt. So earlier when we discussed, so here they have told us we need to assume ideal diode. That's why we are not considering the diode forward voltage drop. Otherwise, we need to add the diode forward voltage drop also. Okay. So we discussed these equations. From here only we can yeah, yeah, these equations. So this first equation, the second one, and from here we got this relation for Rm, and this Vi plus IMRM plus VDM, this was the voltage across the switch. And we also discussed that this should be the voltage rating, this should be lesser than the voltage rating of the switch. So that's what we have written here also. The diode voltage drop is not considered because the diode is ideal here. Okay. So this is the switch voltage. Right. So I think this is our last question. If you have any doubt, you can ask. So the last the assignments, are you able to solve the last assignments? Are you facing any difficulty or like they are easy?
We tried hard and got some good marks.
Acha. Okay.
Madam, I am facing difficulty.
Okay. So are you from electrical background or some other background?
Ma'am, I am from electronics background.
Acha. Okay. So like whatever I discuss in the class, can you understand or you don't understand any part? Actually, in
Mm,
2 hours, it is a bit difficult to cover everything. So, because I need to discuss these numericals also. But you can, if you have any specific doubt in any point or anything, you can ask. You were saying something.
Can I ask later also, ma'am? Is there any possibility apart from this
Sorry?
session? Can I ask
Uh,
later also, or only
ha,
during the
you,
session?
in the next session also you can ask.
Okay, okay.
Ha. Or if you have any doubt regarding your assignment also, you can ask.
Yeah.
Any question or any concept, whatever it is, you can ask.
And how to find the resistor rating, ma'am?
So
Power rating.
power rating, that's what, okay. So actually, practically, so IM value you will have to find out. Okay. So when you will design this transformer, you will know the LM value. At least you will know the self inductance, right? If you have this primary and secondary winding from LCR meter, you can find out what is this LM value. And if you know this LM value, you can find out this IM value. If you know LM and IM, the energy stored in the LM will be what? The energy stored will be
Half LI
half
square.
Lm Im square. So your resistance power rating should be greater than that. This is for practical scenario. Here they have provided the Lm value in the problem. But practically, whenever you will wind a transformer, you will get to know what is your self inductances of primary winding and secondary winding, right? So you can measure that. Then if you have that value, and you can calculate the Im value for a particular operating condition where your D is fixed and Vin is anyway fixed. So then you can find out half Lm Im square, and that will be your resistance power rating, right? So basically, for the transformer, a practical transformer will have some leakage and some mutual inductance, right? So usually we neglect the leakage inductance, but practically there will be some leakage. So your self inductance is the sum of this leakage inductance and the mutual inductance. But as your leakage is usually much smaller than the mutual inductance, so you can take the self inductance only as your Lm, right? So for magnetizing inductance, you can take the self inductance value and you can calculate Im value. Is it fine?
Yes, ma'am. Yes. Thank you.
Okay, okay. Chalo. Okay, bye. Thank you for joining. We will meet next week.
thank you, ma'am.
Thank you. Thank you.
Can you provide PDF?